We're given a parabola, we're told the equation, and the fact that it varies between 0 and 10. And then we're interested in rectangles drawn underneath the parabola. The bottom edge lies on the x-axis, as we can see, and the top left lies on the parabola in all cases. Some examples are shown. Now, in some of the cases, the top right vertex does not lie on the curve. For this one with the lowest height, it does. We're told that the x-coordinate of the top left vertex is A. So let me just imagine calling this one A. Then explain why the width of such a rectangle must satisfy w less than or equal to 10 minus 2a. Now that means that this length here is a, because it's between 0 and a. And we must remember there's a line of symmetry about a parabola. In fact, it's in between the two roots. So here it's going to be x equals 5. And so it would be possible to extend our rectangle at most to the very corner here, because remember it has to lie underneath. And if I draw a line coming down, then this distance would also be a. And therefore, the x-coordinate itself would be 10 minus a. So the width is going to have to be less than or equal to 10 minus a, which is this distance here, minus a, which is that distance there. That will give us our overall width, which in this case is going to be here to here. So therefore, w is less than or equal to 10 minus 2a. So I've said a lot verbally here. I think writing a few things down is good. So by symmetry, the top right vertex can have a x coordinate of at most 10 minus a. Okay, it could be lower, like it is in our example, in fact. And therefore, actually, this kind of follows from that. So I think that's enough of an explanation. We're now asked to find the value of a that gives the maximum area for such a rectangle. So the height of the rectangle, if the top left vertex has an x-coordinate of a, we can just substitute a into our y to get a half a times 10 minus a. Therefore, the area is going to equal w times h. So we've already said that we said that w has to be less than or equal to 10 minus 2a, so the maximum width is going to equal 10 minus 2a. And therefore the maximum area is going to equal half, it's going to be base times height, so 10 minus 2a times a half a 10 minus a. All right, let's keep going with this. So I'm just going to move down the page actually to the bottom. This is now part B still, B continued. So this maximum area, what we can do is actually times the bracket by a half to give 5 minus a times 10 minus a. I'm actually going to bring the a to the left-hand side. And now I'm going to expand this out. So it will be a times 50 minus 5a minus 10a, so minus 15a plus a squared, which if I reorder it so the higher order terms to the left, it'll be a cubed minus 15a squared plus 50a. Now, let me just clarify this maximum area. It's the maximum possible area we can make for a specific left-hand x coordinate. Because remember, we could stop the rectangles shorter if we wanted to, but it's if I make it go the entire way. We still want to find kind of the value of A that gives you the maximum area as such. I feel like this maximum area is writing that is a little bit confusing, but it is the largest area that we can have for a particular value of A. So I'll just kind of call this capital A for now. And what I'm interested in doing is finding the stationary point, the maximum value. So dA by dA. This equals 3a squared minus 30a plus 50 equals 0 for max. Right, now we could try to factorize this. It doesn't look particularly nice. And in fact, it doesn't factorize. So if you do try, I mean, you'd have to go with 3a and a. But you'd quickly see with different factors of 50, there's no way we can get a 30a here. Let's go to the quadratic formula. So a is going to equal minus b, which is 30, plus or minus b squared, which is 900, minus 4ac, which is 4 times 50, 200 times 3, 600, all divided by 2a, which is 6. This becomes 5 plus or minus the square root of 300 over 6. Let's just simplify square root of 300. It's going to be 10 root 3 because it's square root of 3 times the square root of 100. So 5 plus or minus 10 root 3 over 6 becomes 5 root 3 over 3. Now we have two values for a, but we've got to remember that, actually this here would be one of my minimum rectangles. And here a is actually equal to nearly 5. We can't have a more than 5, in fact. Yeah, you can't start it here, for example, because you always start it to the left of the peak. So what I'm trying to say is a has to be less than 5. So we can reject 5 plus 5 root 3 over 3. A is going to equal 5 minus 5 root 3 over 3. Note that we don't have to prove it's a maximum, it's enough to leave it like that. On to part C. We're given that the rectangle must now be a square. Find the value of A that gives the maximum area for such a square. So for our square, we must have that the height is equal to the width. So to get the maximum area of the square, we need the width to be as big as possible. So we need it to equal 10 minus 2a. And it's got to equal the height, which is the value of our function. So we substitute in for a, it's going to be again a half a 10 minus a. All right, we've got another equation to solve. So this time I'm going to multiply through by 2 to make it 20 minus 4a is equal to a 10 minus a. That means 20 minus 4a is equal to 10a minus a squared. So a squared minus 14a plus 20 is equal to 0. Again, this won't factorize. If you try it, it just won't. So we need a quadratic formula. A will equal minus 14, so 14 plus or minus 14 squared, which is 196, minus 4ac, 4 times 1 times 20, so 80, square rooted all over 2. 14 plus or minus, this is 100 and 16, I think. I'm going to divide this one by 2 and this by root 4. So if I have 116, I'll get 50, 58. If I have it again, I'll get 29. So my final answer is going to be A is equal to 7 plus or minus root 29. Again, reject the positive because it has to be less than or equal to 5. So A is going to be 7 minus root 29. That will give us our maximum area of a square. Finally, we're given that the area of the rectangles is fixed at 36, and we have asked to find the range of possible values for A. So note now, we don't actually have to use the whole width like to the endpoint. Okay, that's if W hits its maximum. We might be able to create this area by creating a rectangle such as that. So the first thing that I have is that, this is part D, is that W times H must equal 36. Now remember, we know what H is in terms of A. It's going to be a half A 10 minus A. So therefore, W equals 36 over a half A 10 minus A. And we also have that W is less than or equal to 10 minus 2A. That was one of our conditions from before. So I can actually create an inequality. I've got that 10 minus 2A. That's my, so sorry, that W, oh wait, other way around. So this is now 36. So 36 over a half A 10 minus A, because that is my value of W, is going to be less than or equal to 10 minus 2A. We formed this inequality to solve. Now remember, I'm only interested in when the function is positive. Okay, that was it from the start. I mean, it could equal 0 here, but then that wouldn't give an area of 36. So I can ignore that and I can just treat it as being positive and multiply through. Because remember, you have to change the sign if it's negative, but we're only dealing with situations where this is positive. So 36 is less than or equal to a half A 10 minus A 10 minus 2A. I'm going to times through by 2. So 72 is less than or equal to A. And then I'm going to expand my bracket. 100 minus 20A minus 10A plus 2A squared. Multiply again, 72. Okay, I can combine this to minus 30A. So 72 less than or equal to 100A minus 30A squared plus 2A cubed. Therefore, 2A cubed minus 30A squared plus 100A minus 72 will be greater or equal to 0. We're getting there. We've got a cubic inequality to solve. Actually, there's a common factor of 2, so I can now divide through by 2. A cubed minus 15A squared plus 50A minus 36 is greater or equal to 0. Right, let's solve this. So just like for a quadratic inequality, we're going to actually solve it equal to 0 first. I'm going to get rid of the inequality sign, and then we'll draw a sketch of the function and look at where it's greater than 0 as well. Okay, we're not given any information here, so we're going to have to try to find a factor. Minus 36 is a little bit awkward. I mean, so I can call this thing f of x. So let's try f of 1. We get 1 minus 15. See, this is quite an easy one to put in. Plus 50 minus 36. And minus 15 minus 36 is minus 51. So we do get 0 here. So straight away, we're okay. We've got one. By factor theorem, a minus 1 is a factor. Okay, now a method of your choice to work out the remaining um, factor. I like to just go with polynomial division, tried and tested. You might be able to do it more quickly. But I like just getting a remainder of 0, and then I know I've not made a mistake. So I'm going to get a squared, and then a cubed minus a squared here, subtract, gives minus 14a squared, so minus 14a. Sorry, I should have wrote that down. Multiply back through, plus 14a. Subtract 36a minus 36, so plus 36 here. And we get 0. So a minus 1 times a squared minus 14a plus 36 is equal to 0. Back to trying to factorize this quadratic. Again, it doesn't. So I just now need to focus on setting this equal to 0. And back to the quadratic formula. A will equal 14 plus or minus 14 squared, 196, minus 4ac, 4 times 36 is, we'll double it again, 144, square rooted all over 2. This is going to become 7 plus or minus. Subtracting these gives 52. So I get the square root of 52 over 2, or the square root of 4, which gives me 7 plus or minus root 13. I think a sketch is good here. So I've got a cubic, and I know that one of the roots is 1. One of the roots is 7 minus root 13. That's going to be less than 4, so it's around, it's 3 and a bit, maybe here. And then I've got one at 7 plus root 13 as well. Remember, that is more than 5, so that couldn't possibly be a solution. I also know that my cubic goes through minus 36. So it's going to come up, down, then it's going to be negative. So we're interested in where this is greater or equal to 0. Remember, we just kind of left that part for the time being. And so now we can look at our graph and see it's between this range, and therefore overall 1 is less than or equal to a, which is less than or equal to 7 minus root 13. Okay, interesting question here. We've got these rectangles. We showed the first inequality. We used calculus to optimize the area of a rectangle, although we didn't actually find the maximum area of the rectangle. We found the value of a that gave the maximum area, but we could then find the maximum area. We looked at when the rectangle becomes a square and how that changes things. Working in terms of surds, it's quite hard to see how close all these values are together, to be honest. I've not really spent time on that. And then finally onto D, we fixed the area at 36, and also recognized that A is still on the top left vertex, but the top right of the rectangle doesn't have to be on the parabola. And so we're interested in the different ranges of A. There's going to be lots of possible values. So we constructed an equation, linked it to the inequality, created this inequality that became a cubic inequality, solved it equal to 0, found the factors, drew a little sketch, and saw that A could vary between these two values. Well done.